Hello, everyone, and welcome to our presentation. We are Team Blue Mac from Pratt School of Engineering at Duke University. I'm Yong.
I'm Mohammed Ahmed.
And I'm Noemi.
And I'm Yongjali.
We would like to introduce our project, the CRU-TCH system. This innovation is aimed at revolutionizing mobility aids through advanced engineering principles to enhance comfort, responsiveness, and health for users. Currently, traditional crutch designs lack dynamic responsiveness and adequate shock absorption, often leading to user discomfort and upper body strain. Our crutch project aims to address these limitations by integrating a mass spring damper system, offering adaptive damping and propulsion to enhance mobility and user comfort across diverse needs. Our project stands for Comfortable, Responsive, Universal Technology for Crutch Health. The aim is to address the shortcomings of current crutch designs by integrating a mass spring damper system to improve shock absorption, energy transfer, and user comfort. Traditional crutches fail to provide sufficient shock absorption and energy efficiency, leading to discomfort and strain for users. Our project seeks to solve this by integrating a mass spring damper system to enhance ergonomics and adaptability for diverse user needs. Here, you can see how the mass spring damper system works in a standard worker. This illustration helps us understand how these principles can be adapted for other mobility devices like crutches. By applying mass spring damper system to the crutch, we designed a 3D CAD model of our crutch. We placed the spring under the shoulder pad in order to improve propulsion, and we put a shock absorber at the bottom of the crutch to improve energy transfer. By incorporating the mass spring damper system into our crutch design, we provide users with shock absorption tailored to their specific loads. This adaptation ensures both comfort and efficiency in motion. We used a mathematical approach to model the mass spring damper system. This equation represents the dynamics factoring in mass, damping, and stiffness. Applying Laplace transforms, we solved for displacement as a function of time under various force inputs. This is the Simulink block diagram of mass spring damper system. We use Simulink block diagram to simulate mass spring damper system and plot a visual graph. In order to grab a general understanding of the mass spring damper system in our crutch, we implemented simple simulations as shown here. We got a left-hand side graph when the system is undamped and the right-hand side graph when the system is damped. Simulations demonstrate how different damping and stiffness values affect displacement over time. By tuning these coefficients, we aim to optimize the crutch responsiveness to user loads. For example, higher damping reduces overshooting, while varying spring stiffness adjusts energy return. After we finished the simulations, we planned experiments to show our device functionality. Our experiment plan includes analyzing ground reaction forces to optimize the spring and damper coefficients. This process involves simulating and testing the forces exerted during crutch use, ensuring the system adapts to different users effectively. The second experiment compares shoulder's trajectory across different designs. With optimized damping and propulsion, our design achieves smoother and more natural motion as seen in trajectory C. This highlights the potential ergonomic benefits of our crutch system.
So for the experimental setup, we wanted to use a motor in order to be able to provide a customizable experience for the user where they would be able to adjust the stiffness of the damper themselves. And we wanted to do this just to overall make it easier to adjust for things like perhaps different terrains or overall just offer more flexibility for the person who may be recovering from perhaps different injuries or depending on their circumstances. And even though we weren't able to implement this into our crutch, we were still able to successfully get our motor working using a pretty compact and efficient system. So as we can see in the images right here, we ended up using the Xiao ESP32S3 as well as the A4988 stepper driver using a computer interface. And for future work, if we would have had a little bit more time, we would have liked to have implemented our motor into our crutch using a more simple control mechanism, like perhaps having it be a button operated instead of using the computer interface, since we really want to make sure that our crutch project is as simple and as versatile as possible. We really think that having a simpler interface will help increase the accessibility and the usability for the person that's using our crutch. And it also plays into our goal of making sure that our crutch is very lightweight and overall is just a very ergonomic design. So another component that we worked on was the design of our load cells. And the purpose of using our load cells was to make sure that we were evaluating and comparing the forces that were being exerted using both the regular crutch as well as our crutch using the spring damper system. And for our setup, initially we ended up using Arduino Nano to the HX711 amplifier to load cells. And for the most part, the setup of the system was fine. The load cells were able to communicate well amongst each other, but when it came to transmitting data wirelessly, that's when we started to run into some issues. And we kind of thought about keeping it with the Arduino Nano, but we realized that it was overall just a bit more complex to implement and it did involve more components. So we then ended up talking and deciding to kind of swap everything over to the ESP32. And when we did this, everything worked and this enabled wireless data transmission pretty seamlessly. And overall, it was just a lot better. And after doing this, we then ended up focusing on developing real-time data logging to make sure that we were capturing the different force measurements as well as integrating real-time plotting just to be able to better visualize and analyze these forces. And in this slide, we can see one of our team members, Young Jae, walking with our crutch when we ran our experiment and how we have real-time data logging on our left side corner as well as real-time plotting that we can see in our graph that's being developed when YJ is walking back and forth for a few minutes.
ESP32 to ESP32 communication was very important for our Crush project. The ESP32 to ESP32 communication allows two ESP32 boards to exchange data wirelessly using protocols like ESP Now or Wi-Fi, enabling them to communicate directly without a central router. In Crutch project, ESP32 to ESP32 can be used for wireless transmission for sensor data like accelerometer readings or load cells. This enables real-time monitoring for users' movement and health data, improving the system efficiency and responsiveness. Here we have used accelerometer. So accelerometer is basically a sensor which measures the acceleration along the XYZ axes. We have used MPU 6050 accelerometer. The accelerometer data is read by the ESP32 and processed, and after that it's wirelessly transmitted to the other ESP32 by communication via I2C, which is connected to the laptop. So this helps us monitor walking patterns, identify abnormalities like uneven strides or improper crutch use, and ensures user safety by providing feedback. As you can see in the video on the left hand side of the video, the accelerometer readings are received by the ESP32, and on the right hand side the data is being sent to the other ESP32 wirelessly.
So for our experimental results, we ended up noticing that after looking at our graphs, the crutch showed that the one that we created showed reduced peak forces when compared to that of the regular crutch. So here we can see for our crutch, we had a 140 Newton force versus the 600 Newtons for the regular crutch. So that's a overall pretty big difference. And what this pretty much shows us is that our spring damper system does provide shock absorption and is able to absorb some of the impact and distribute these forces out more evenly. And what's really nice seeing this is that it does help us prove how our crutch does cause less strain on the user, and this would be overall just more comfortable for them to use versus that of a regular crutch that they can find on the market.
Okay, I'll briefly explain the principle of operation of our crutch first. From the top of the figure on the left, we split it into sections A and B respectively. Section A uses spring. Part 1 is free to glide along the frame of the crutches, and Part 2 is firmly secured to the frame. The springs connect these two parts, which are responsible for relieving the impact force when the crutches touch the ground. For Part 2, fixing this part was a major challenge because it had to bear all the load on the user. We will discuss in detail later on few pages. Section B is the damper part and serves to mitigate the initial reaction force transmitted from the ground to the user's armpits. Now I'm going to talk about the design of four parts from the top of the figure on the left. All parts were modeled using Autodesk Fusion and 3D printed. First, let me explain the design of Part 1. When designing this Part 1, I was most concerned with the gap between the two holes. If this gap is too narrow or wide, it will not only be able to fit on crutches, but it will also be stuck between the two frames of crutches, making it impossible to move smoothly. After several experiments, comparing the distance between the two cylinders of the crutch, the optimal distance between the two holes was set to be 3 mm longer than this distance. In addition, since the upper part of Part 1 touches the user's armpit, a curved design is applied to increase the user's feeling and to apply the rubber pad. There is a square hole in the middle, and it requires additional shape optimization to minimize weight and material cost. Part 2 design is characterized by semicircular holes on both sides that have the same diameter as the cylinder part of the crutches, because Part 2 needs to be attached to the cylinder as much as possible. Furthermore, if Part 2 length is too long, the frame of the crutches will be spread out to both sides, making it impossible for Part 1 to move smoothly as Part 1 is stuck between the frames. Through several experiments, this length was set 2 mm smaller than Part 1's length to both sides. Also, the shape optimization will proceed for this part too. When designing Part 2, there were two things that were most important. First, it's a strong holding force because it's the part that has to bear the weight of the user. The second is the possibility of a quick position change because if a different length of spring is applied depending on user's weight and body shape, part 2 must be moved up or down and fixed again accordingly. To do this, we considered four methods. In the case of fixing part 2 with a clamp, it was difficult to fully adhere to the cylinder, and in order to change the position of part 2, it was inconvenient to rotate the screw to move the clamp position. In the case of extending the length of part 2 to both sides, it was rejected because it could affect the movement of part 1 if it was extended a lot for a strong fixing force. Also, drilling was rejected as well because the movement of part 2 became impossible. The final method was to remove and attach part 2 using Velcro. It was finally adopted because it is the simplest and cheapest method for both strong fixation and fast movement. Parts 3 and 4 are applied to ensure that the damper and rubber packing are secured without shaking respectively. Next, it is the result of shape optimization in parts 1 and 2. The analysis was conducted by applying the same conditions as when using crutches in practice, and it was found that shape optimization is possible for the middle part of each part as shown in the figure. Finally, The directional field research is the motor. The damper shown in the figure on the left can be rotated to adjust the strength. By connecting this part to the stepper motor using the parts shown in the middle figure, the damping force strength can be adjusted in real time to achieve optimized impact force mitigation. This is the presentation we have prepared. Thank you very much for listening, and if you have any questions, please contact us via email or other ways, and we will reply quickly. Thank you.